Hello. Yeah.
Yes, sir. Yes, sir.
Yeah. We'll start then. My screen is visible now. Full screen.
Yes, sir.
Yes, sir.
Okay then. So, in today's lecture, we are going to discuss about fuel spray in CI engine. Okay, the spray phenomenon and the spray structure we are going to study today. And the outline of the presentation is like this. So we'll start with the different phases of spray formation. Then we'll discuss about the schematic of fuel spray in a diesel engine. Then what are the factors that are responsible for the fuel droplet size? And we'll go for the schematic of diesel spray. And diesel spray, when we are going to have different air motions. Like let us say if you are going to have a swirl, then how does this diesel spray will appear? And some of the images of fuel spray for single hole present in a fuel injector, multiple holes in a fuel injector with air motion, without air motion, and then for indirect injection of diesel fuel. And finally, we are going to solve a numerical problem on nozzle design, right? Fuel nozzle design. So this is the agenda for today's lecture. See, if you see the fuel nozzle, right? The diesel fuel injector, it appears like this. In general, so this complete structure or the complete system, we call it as a fuel injector. In this, we have one important component called fuel nozzle. So at the bottom, if you see, so this is what we call it as a fuel nozzle. And the complete system, we call it as fuel injector. At the tip of the fuel nozzle, we will have a small hole, which we call it as an orifice, through which the fuel spray is going to be happening. Okay. So this diagram, if you see, so this is the fuel, this nozzle part, right? And here you can see a small opening, which we call it as orifice, through which the fuel is going to be sprayed. Okay. So from the high pressure pump, high pressure fuel injection pump, fuel will enter into the fuel injector and it is going to enter through the fuel nozzle. Finally, through the orifice, it is going to come out with very high pressure. The pressure of the fuel injector will be something around 200 bar to maximum of 2000 bar. That depends upon the design of the fuel injector. Okay. Yeah. And coming to the, let us recollect the valve timing diagram which we have studied for a 4-stroke diesel engine. In this valve timing diagram, we want to determine what is the time that is required for injecting fuel. During fuel injection, how much time is normally taken by fuel injection process. That we also call it as a pulse width of the fuel nozzle. Okay. So now in this diagram, if you see, that day we have discussed in the earlier lecture, the suction stroke, compression stroke, expansion stroke, and finally the exhaust stroke. And if you see, before the end of the compression stroke, fuel injection starts, and the fuel injection stops. This is the injection stops, right? This is starting of the fuel injection, and this is the fuel injection stopping. So this is the crank angle during which fuel injection, the fuel nozzle is open and the fuel spray is happening inside the engine cylinder. Okay. So now this time period we want to determine in terms of seconds, right? So this crank angle turned during the fuel injection will be something around 20 to maximum of 40 degree, right? Generally from 30 to 40 degree it will be there. In some cases you will find around 25 is also possible. The fuel injection during the crank angle turned during fuel injection will be something around 30 to 40 degree. Okay. So now let us calculate how much time it takes for fuel injection. Assume a 4-stroke engine which is operating at 3000 RPM. And if the 4-stroke engine is going to operate at 3000 RPM, then the number of cycles per minute is going to be divided by 2, right? Because for every 2 revolution of the crankshaft, we are going to have one complete cycle of operation. So the number of cycles per minute is going to be 1500 cycles. So in terms of second, if you convert, so 1500 divided by 60. So that will come to 25 cycles per second. And the time taken for fuel injection per cycle, right? So number 25 cycles per second. So the time taken in seconds, right? For one cycle, for completing one cycle is 0.04 seconds, right? 1 divided by 25 is the time for completing one cycle of operation. And for one cycle of operation, the crank, it will rotate or it will turn 720 degree, because two complete revolution of the crankshaft, which is 720 degree crank, and for which it takes 0.04 seconds. Now assume that if you are going to have fuel injection for a period of 40 degree of crank angle turn, right? For crank angle rotation of 40 degree, what is the time that is? What is the time for this 40 degree crank angle turn, and which is nothing but the fuel injection time period. So the fuel injection time period, it comes to be around 0.22 milliseconds. Okay. So the fuel injection time is going to be in terms of milliseconds. This is what I want to tell you now. Okay. So in a very small time period, in milliseconds of time period, the fuel injection has to take place. And when the fuel is going to be sprayed or injected into the engine cylinder, in the case of diesel engine, it has to mix with the air, and it has to undergo atomization, mixing of air and combustion, right? Everything has to be. So it is very, very important, the timing and the quantity of fuel injected and the spray pattern of the fuel that is being injected. So these are very important for complete combustion of the fuel. So coming to the different phases of spray formation, right? So when let us say it can be a electronically injected fuel injector, or it can be a mechanically open fuel injector. These are some of the phases of spray, right? Initially, let us say when the fuel nozzle opens, right? So at the beginning, the pressure drop will be less, right? The pressure drop between the orifice, the pressure drop across the orifice is going to be less. Because of that, the fuel is going to come out in the form of droplets. This is during the initial stages. So we will be getting almost something like 4 to 5 droplets of the fuel will be sprayed into the engine cylinder. And subsequently, what will happen is that there will be a continuous flow of this fuel in the form of liquid, right? To a certain extent. This is after the droplet formation, then we'll be having the continuous liquid, right? To a certain distance. Then after that, that continuity will break. Okay. So this we call it as breakup distance. I will tell you in detail the breakup distance. So a stream of fuel in liquid form, it is going to emerge from the orifice. Okay. And that it is going to, again, this continuity is going to be disturbed, and you will have the spray of the fuel or vaporized fuel is going to be there beyond this. So that initial distance we call it as L1, right? Where we are going to have the fuel in liquid state, right? That will be occurring at the core. Then subsequently, with further increase in the pressure, what will happen is that this stream of liquid, it is going to encounter the resistance offered by the high pressure air present inside the engine cylinder, right? At the end of compression or about to complete the compression stroke, this fuel we are going to inject, and inside the cylinder we are going to have very high pressure air, right? And when the fuel is going to be injected, it has to overcome this pressure of the air, right? And the spray has to penetrate into the air. Okay. So the distance of this point where this breakup, right? When we inject the fuel, so it reaches certain distance, and then the liquid stream, it will break up, right? So that distance we call it as breakup distance. Okay. And in subsequent slides, I'll be telling you about the primary breakup and the secondary breakup. Now, whatever we are discussing is the primary breakup. This primary breakup is the distance of this point where the stream of liquid, right, which gets disturbed. Okay. So the distance from the nozzle orifice to the breakup of the liquid stream of the fuel. So that distance we call it as the breakup distance, or this is also called as primary breakup distance. So now if you see from the nozzle orifice, because of the subsequent increase in pressure, this is the stream. Okay. And beyond this, the dispersion of the liquid starts, and you will try to see the formation of a cone, right? So the dispersion, it is going to diverge and the formation of the cone is going to happen. This complete distance we call it as the breakup distance. Okay. So now with the further increase in the pressure, in the next stage what will happen is that this L3 distance will get reduced and it will come to L2, right? So if you see in this diagram, so up to this, the earlier it was up to this, now the breakup distance reduces, right? In the next phase of the spray pattern, if you see the breakup distance will reduce. Okay. So then in the next stage, in the fifth stage, right, initially we had the droplet formation, then we had the stream of liquid, then we had the breakup distance, then we had the reduction in the breakup distance, then subsequently in the fifth stage we will be having the formation of the spray cone. So this spray cone formation will begin. And in the last stage, what will happen? This spray cone will be widening or it will be diverging, and this spray cone and the apex of the spray cone will get attached to the orifice. So here you can see, right? So here apex will be beyond this, inside the your orifice. Here you can see it will be from the orifice. It will attach, the apex of the spray cone will attach with the orifice. Okay, so this structure is what we call it as spray cone structure, and this is very, very important for complete combustion of the fuel. Okay. So now coming to the when we are allowing the fuel to come through an orifice, right? We are allowing the fuel with very high pressure, with the pressure in the range of 200 to maximum of 2000 bar. With a very high pressure, when the fuel is going to pass through this orifice, it is going to come out with a high velocity. To determine the velocity of the fuel that is issuing from the orifice of the nozzle, so we are going to use this formula. This is nothing but your velocity. If you want to calculate, how will you calculate normally? Through an orifice, CD into under root 2GH, 2G into H. H is nothing but the pressure drop across the orifice. So that H, if you know the pressure inside the your fuel injector and the pressure inside the cylinder, so that difference in pressure is going to be the pressure drop. So in terms of the pressure of the fuel injector and the pressure of the engine cylinder, if you want to express, then this pressure drop H equal to P by rho G. So that is what is written here. So that delta H, 2GH, H is the pressure drop in terms of meters of the liquid column. So that if you want to express in terms of direct pressure, then it is pressure of the injector minus pressure of the cylinder divided by rho G, P by rho G, no? So already 2GH is there, that G and this denominator G both are getting cancelled. So you will get finally in this expression. So if you want to determine the velocity of the fuel that is issuing from the orifice of the nozzle fuel injector, then it is given like this, CD into under root 2GH, where H is expressed in the form of P by rho G. Okay. So coming to the schematic diagram of the diesel spray. So here you can see the fuel that is being issuing from the or getting sprayed from the fuel injector, and this is what we call it as the spray cone, right, or the diesel spray. Now in detail, if you see within this, so this is a complete diagram. Some of the terminologies related to the diesel spray is given here, or the fuel spray is given here. So as the injection is happening through the orifice of the fuel nozzle, so at the center, right, at the center will be the fuel in liquid state, right? A stream of fuel in liquid state is going to be there at the center. Okay, and subsequently in the next layer adjacent to this, from the center of the fuel spray adjacent to this, we are going to have fuel fuel droplets will be there, right? Here we will be having fuel droplets. This is liquid fuel in liquid state. Then beside this we are going to have fuel droplets, and at the extreme end we will be having fuel in vapor form. Okay, so the extent to which the fuel in liquid state or the stream of fuel liquid, so that is going to be there, that we call it as the breakup distance, right? This is what we call it as breakup distance or primary breakup distance. Okay, and remember, when the fuel is going to be issuing from the orifice and with very high velocity is going to come out, and it reaches certain distance, right? So from here to the maximum distance it reaches, that we call it as the spray penetration. This is spray penetration length. This is spray penetration length. This is the breakup length. Breakup length is the distance up to which the fuel will be in liquid state. Okay. At the core, at the center of the spray, right? Only at the center of the spray, we will be having that fuel in liquid state. And the complete distance reached by this spray, so that we call it as the spray penetration. So this is completely surrounded by the compressed air, and this fuel is going to be sprayed and it is going to reach a certain distance. That complete distance is called spray penetration distance. Okay. So the angle formed by this spray cone, the angle formed by the spray cone is called the spray angle or spray cone angle, which is given by the notation theta. Okay. So at the center, at the core, we are going to have the liquid stream, then the liquid droplets, and we are going to have the vapor of the liquid. Okay. So now in detail, if you see the spray breakup, so this is the fuel nozzle, and the fuel is going to come out from the fuel nozzle, and this is what I am referring to. At the core, we are going to have the fuel in liquid stream, right? The fuel stream in liquid state. Okay. So this distance we call it as a primary breakup distance. This we call it as primary breakup distance. And from the primary breakup distance to the complete spray, to the spray penetration full length, from here to the spray penetration length, that distance we call it the secondary breakup. So this is primary breakup and this is secondary breakup. Okay. And this complete length, hello. Hello, am I audible? Hello.
Yes, sir, audible, sir.
Audible, no? Please, others, please mute yourself. Others, please mute yourself. Okay. And apart from this, there is one more parameter in the fuel spray, which we call it as Sartor mean diameter. So there is a parameter called Sartor mean diameter. When the fuel is going to come out from the spray nozzle, when the fuel is going to come out from the spray nozzle, the droplet size is going to vary. The droplet size is going to vary, and to measure the mean diameter of the droplet. Hello, please mute yourself. There is a lot of disturbance. Hello, mute yourself. Okay, so to determine the Sartor mean diameter, the total volume of the fuel spray, so that we have to consider, divided by the surface area of the fuel spray. So that will give you an average diameter. So that is the average diameter of the fuel droplet. Okay, average diameter of the fuel droplet. Okay, and coming to the let us conclude everything regarding the spray structure and the spray formation. So the spray from the orifice, that is issuing from the orifice. So there are three regions. At the inner core, we are going to have the denser liquid. Okay, that is going to be at the inner core, at the axis of the fuel injection. Then it is going to be surrounded by a cone of fuel droplets. Hello, please mute yourself.
Sir, you can mute all attendees instead, sir.
Yeah, I'll try to do. Mute all. Melo. Yeah. Yes. Yeah, I have muted everyone. Okay. So when the fuel is going to be sprayed from the orifice, when it is going to issue at the axis of the fuel spray, we are going to have the denser fuel. Then followed by that, that is going to be surrounded by a cone of fuel droplets, and at the outer periphery of the spray cone, we are going to have the vaporized fuel. Okay, and remember, the droplet size of the fuel is an important parameter, right? So that plays major role for the complete combustion of the fuel. If the droplet size is bigger, then we'll have higher penetration. The penetration depth of the fuel into the compressed air will have the higher penetration depth into the compressed air. And if the droplet smaller, right? If the droplet size is smaller, then we'll have the better mixing and the evaporation of the fuel is going to be better. Okay. So as per under ideal condition, we say like we'll need to have a fuel spray of less than 5 micron. This is under the ideal condition, but in reality, we'll be having more than 5 micron. Almost 10 micron we'll be having. More than 10 microns we'll be having in reality. Okay, but under ideal condition, we say like theoretically we should have a fuel droplet size of less than 5 micron. So the factors that affect the fuel atomization are the droplet size. What are the factors that are responsible for the droplet size? The mean droplet size decreases if the injection pressure is more. If you are going to increase the pressure, then the fuel droplet size is going to decrease. Right? This is one parameter. And also the fuel droplet size decreases with the increase in the density of the air. Higher the pressure at which the air is going to be stored in the engine cylinder after compression stroke, its density is going to be higher. Higher the density of air, then the droplet size, because it has to penetrate. When it is going to penetrate, it is going to get disintegrated. The fuel is going to get disintegrated and the droplet size will be smaller. So droplet size decreases with increase in air density. And the droplet size increases if the viscosity of the fuel is, if the fuel viscosity is high, when it is going to come out, then to disintegrate the fuel into droplets, it is difficult. So size of the fuel droplet will be bigger or higher, right? And the size of the droplet also depends upon the orifice size. Higher the orifice size, then the droplet size also is going to increase. Okay. So coming to the schematic of, or the temperature variation within the spray cone angle, within the spray cone or the fuel spray, the spray structure of the fuel, what are the temperatures involved if you want to see. So let us say horizontally we have represented here. Fuel injection is being represented horizontally here. So this is the injector. From the nozzle of the injector, fuel is going to be sprayed. So listen carefully. See, when the fuel issues from the orifice, its temperature will be something around 350 Kelvin. Okay, assume that it is coming out at a temperature of 350 Kelvin. Now, when it comes out, the fuel jet that is coming out from the orifice, that is surrounded by the compressed air, right? That compressed air also, if you are going to have air motion, so there will be swirl or tumble that is going to be there inside the engine cylinder, the movement of the air. Okay, that air temperature is something around 950 Kelvin. So closer to 1000 Kelvin. So we are going to have air temperature, whereas the temperature of the fuel that is injected from the nozzle is at a temperature of 350 Kelvin. Okay. So now as the fuel diffuses or penetrates into the compressed air, the pre-combustion starts, right? The oxidation is going to start, and here we are going to have more amount of fuel and less amount of air, because less amount of air is interacting here at this region, and this is the pre-combustion region where the temperature is something around 825. Subsequently, its temperature is 1600 Kelvin. Okay. So here also it is not complete combustion. Remember, this is also not complete combustion. This is the region where we are going to have the complete combustion. So this is pre-combustion. This is the intermediate combustion. In the intermediate combustion, combustion is not complete. So the products are going to be carbon monoxide. It is not carbon dioxide. Only when the combustion is complete, we will have carbon dioxide. So here combustion is not complete. So the products of combustion are going to be carbon monoxide, and hydrocarbons are not burned completely. So unburned hydrocarbons are going to be there, and soot particles are also going to be here. Okay, and the temperature in this region is something around 1600 Kelvin. So this is the region where we are going to have the complete combustion of. When we are going to have complete combustion of the fuel, the temperature is going to be something around 2700 Kelvin. So the temperature when we are having the complete combustion, so the temperature is going to be something around 2700 Kelvin. And at higher temperature in the air, we are supplying air for combustion. Along with the fuel, air is supplied because the fuel is going to undergo oxidation. So in the air, oxygen is present. Along with oxygen in the air, we have nitrogen. Okay. This nitrogen at higher temperature, it reacts, right? Combustion takes place, its temperature is high. At high temperature, the nitrogen present in the air, it reacts with the oxygen and thereby knocks, okay, then unwanted emission from the engine cylinder. Okay. So the emissions, we know that the unwanted emissions are CO, unburned hydrocarbon, and soot particle, and this NOx. Okay. So if the combustion is complete, instead of CO, you will have CO2. Okay, this is a complete schematic of the diesel spray inside the engine cylinder during combustion. Okay. And now let us say inside the engine cylinder, we are having the air motion. Assume that swirl is going to be there. So the air is swirling along the axis of the fuel injection, right? This is the swirl, and we are injecting the fuel from the fuel injector. The fuel injector orifice is this, and we are going to have the primary breakup distance, right? Or in general, we call it as breakup distance, up to which we will be having the liquid stream, right? Without any disintegration, continuity of the liquid stream will be there. Okay, so this is the core. This we call it as the core. Then we will have the droplet. Okay, fuel droplet, and finally vaporization of the fuel will be here. So this is the core, then fuel droplet, then we are going to have the vaporization of the fuel. So now since the air is moving here, right? So this structure of the fuel spray, it is going to get disturbed. It is going to be like this, right? So without any air, let us say assume that we are testing in the fuel injector. In the test setup, when we the test setup will be it will be transparent, right, to determine the spray structure. And when you are going to spray in the absence of air, you can see the profile. So in the absence of air, the air at atmospheric pressure, then the spray will be like this. When the air is moving, when there is air motion because of swirl, then the spray will be, the profile of the spray is going to change like this. It is also going to rotate. Okay. And coming to the some of the diagrams of the fuel spray, right, for different types of engine cylinder with fuel injection, right? Now you consider this is a direct engine system for CA engine with only one hole, right? This fuel injector is having only one hole or one orifice, and there is no air motion, right? This case is for no air motion, right? Quiescent chamber, right? Compressed air is there and there is no movement of the air. So when it is being sprayed, initially it is going to be like this. Then slowly you can see it is getting diffused, and here you can see the diffusion is increasing, and here the combustion starts. The partial combustion. This is complete combustion. Okay. So this is for an engine with a single hole. The fuel injector provided with single hole, and there is no air motion. Now let us say if you are going to have air motion, right? Swirl is going to be there, and it is a single hole nozzle. Okay, so here this is from the center, right? From the center, how it is, the spray is going to be sprayed, right? This is different angle. From the side they have shown. Here this is from the center. From the top, when we are going to spray the fuel through the fuel injector, so here you can see it is getting diffused with the compressed air, and combustion starts, and this is complete combustion. This is for a single hole nozzle with swirl motion in the engine cylinder. Now if it is going to be multi hole, right? So here this is 1 2 3 4. There are 4 holes in the fuel nozzle. So its spray pattern is this, and it is going to diffuse with the fuel and combustion takes place. If it is an indirect injection with the swirl, right, then you will be having a pre-combustion chamber and main combustion chamber will be there. So this is the main combustion chamber and this is the pre-combustion chamber. In the pre-combustion chamber, this fuel is injected, and from here it is going to enter into the main combustion chamber, right? So that combustion pattern you can see in this diagram. So these are some of the pattern of the fuel spray when it undergoes combustion inside the engine cylinder for different cases like a single hole, multi-hole, direct injection, indirect injection. Okay. Coming to the some of the nozzle parameters and spray phenomenon. So if you see some of the values related to the fuel injection parameters are, the fuel will be injected at a pressure of 200 to maximum of the 2000 bar. And air temperature, right, after compression inside the engine cylinder, after the compression stroke, it will be around 1000 Kelvin. And the velocity with which the fuel is going to come out from the orifice, the fuel nozzle, is around 100 to 300 meter per second, and the orifice diameter will be normally of 0.1 to 0.4 mm. And there is a parameter called L by D, that length of the orifice and to the depth of the orifice, length to the diameter, right? So that we can see here, you can see in this nozzle. So this is the length and this is the diameter of the orifice. Okay, length of this, and this is what we call as L by D ratio. So that is also an important parameter. So that L by D ratio will be in the range of 3 to 5, and the droplet size will vary from, practically the droplet size will vary from 100 to 10 to 100. Okay. So some of the parameters when the fuel is going to be injected into the engine cylinder, so it is going to experience drag by the compressed air, and there will be turbulence, and the surface tension of the liquid droplet, and the surface instabilities in the fuel nozzle, and breakup of the your fuel droplet and atomization, and the air that is entering into the fuel spray, and the collision of the fuel spray droplet with the air, and vaporization of the fuel droplet and mixing with the air, pre-flame reactions, ignition delay, and auto ignition. These are some of the features. All this happens when the fuel is sprayed for combustion inside the engine cylinder, right? Now I have told you, like, there are two different types of fuel injector. It can be a mechanical system or it can be an electronic fuel injection system. Whatever may be the your fuel injection system, it can be mechanical or electronically operated. There is a parameter called pulse width, right? Injector pulse width is nothing but the amount of time period during which the fuel nozzle is going to be in open position for delivering the fuel. Okay, so that we call it as pulse width, which is given in terms of seconds. That will be usually in terms of milliseconds. So now let us say this is the ideal case which we want to achieve. That means this is the start of fuel injection, right? The mass flow rate starts from 0 to it reaches this value, right? Maximum mass flow rate, and the same maximum mass flow rate it should remain for a certain time period in terms of milliseconds or in terms of the crank angle turn. In degrees also we can express this. This can be expressed in degrees or in milliseconds. So this is the crank angle during which the fuel is going to be injected, and the end of injection, this is end of injection, then the mass flow rate is going to be 0. So this is start of injection where initially the mass flow rate is 0 and it reaches maximum. Then it is going to remain for a certain time period. Then the end of injection is going to occur. That means there is no mass flow rate. So this is under this red one in the form of a square. Whereas in reality, you will not, you cannot have this square or rectangle, but the profile is going to be like this. So the mass flow rate is going to increase and it reaches the maximum. Then continuous mass flow rate is going to be there, and it reaches the end of injection where the mass flow rate is 0. Okay. So this distance we call it as the pulse width. Okay, which is expressed in milliseconds. So that is what at the beginning of the lecture I have started to tell you what is the time that is involved in the fuel injection. Right? So that is what we have calculated initially. We have considered like a 3000 RPM engine, and we have calculated what is the time that is taken for injection of fuel for a 40-degree crank angle. Okay. So now let us come to a small numerical problem. So you consider this numerical problem. I think like we can solve. We'll solve this numerical problem. Yeah, am I audible?
Yes, sir.
Yes, sir.
Okay,
Sir,
okay.
audible, sir.
Shall we solve this problem?
Okay, sir.
Okay, sir.
So you refer this, and I will go to the given data. So here it is given that they are asking to calculate the orifice diameter and length. So L by D, we were discussing, that length and D, diameter of the orifice, both we are going to calculate for a 4-hole nozzle. So in this nozzle, there are 4 orifices are there, 4 holes are there, and the number of cylinders is only one, single cylinder, 4-stroke engine, and the brake power output from the engine is 25 kilowatt, and it is operating at a speed of 2500 RPM. The specific fuel consumption is given as 0.3 kg per kilowatt hour, and the fuel is having a density of 876 kg per meter cube, and it is injected at a pressure of 150 bar, whereas the cylinder pressure is 40 bar. That means what is the pressure drop across the orifice? In the injector, pressure is 150 bar. Pressure inside the engine cylinder is 40 bar. So what is the pressure drop? 150 minus 40. So 110 bar is the pressure drop. Yeah, 110. And the injection occurs for a duration of 25-degree crank angle. And the L by D ratio is given as 4. coefficient of discharge is given in the form of an expression in terms of L by D. So these are the input parameter. These are the given data. So now if you see the, let us solve this problem. Try to have, you can solve this using pen and paper. So the parameters given are break power is 25 kilowatt and number of holes equal to 4 and the RPM of the engine is 2500 RPM. Specific fuel consumption, brake specific fuel consumption is 0.3 kg per kilowatt hour. Density of the fuel is 876 and the injector pressure is 150 bar, cylinder pressure is 40 bar and the fuel injection is done over an angle of 25 degree, crank angle of 25 degree turn. Okay, crank angle turn of 25 degree. L by D ratio is 4, coefficient of discharge is given in terms of L by D and they are asking you to calculate the value of L and D. Okay, so this is what is given in the problem. Can I change the slide? Note it down.
Yes, sir.
Yes. Okay. So the mass flow rate of injection, right? So they are asking you to calculate the L and D, right? RFS diameter and the length. Okay. So that is there in the cross-sectional area. Diameter is there in the cross-sectional area. So if you know the RFS diameter, then you can calculate L because L by D ratio is given as 4. In the problem, they specified that L by D ratio as 4. So you should calculate any one, either L or D. Let us say if it is diameter of the orifice, then the mass flow rate per injection when the fuel is being injected, what is the amount of fuel that is being injected? So to calculate the mass flow rate per injection, it is rho AV. Okay, this is density of the fuel. This is the cross-sectional area of the orifice and the velocity with which the fuel is going to be injected. Okay, so the orifice, the area of the orifice is pi by 4 d square, where d is the diameter of the orifice. So you can calculate the cross-sectional area. Cross-sectional area of the orifice is pi by 4 d square. And to determine the velocity of the fuel flow that is coming out from the fuel nozzle is CD root 2GH, where H is the pressure drop. Okay, so now we want to determine the mass flow rate of the fuel. Specific fuel consumption is given. What is specific fuel consumption? Mass flow rate of the fuel divided by brake power. So this we know from our basic thermal engineering course. We have studied specific fuel consumption equal to mass flow rate of the fuel divided by per unit brake power. Okay. So from this, what is mass flow rate? Specific fuel consumption into brake power. So specific fuel consumption is given in the problem. Brake power is also given in the problem. So specific fuel consumption is given as 0.3 kg per kilowatt hour. Remember at the denominator here we are having kilowatt hour, 0.3 kg per kilowatt hour. So this brake power is given in kilowatt. So directly you can substitute. Don't convert this into watts. Brake power is specified as 25 kilowatt. Since this is in kg per kilowatt hour, this we can substitute in kilowatt directly. So if you multiply, so this is kg per kilowatt hour, whereas this is kilowatt. So kilowatt will get cancelled. We'll get kg per hour. So the mass flow rate of the fuel is 7.5 kg per hour. Is that clear up to this? Yes, is this clear?
Yes, sir.
Yeah. So this if you convert into this if you convert from into kg per second, you have to divide this by 3600. So this much quantity of fuel per second is being injected. Okay. So this is the total mass flow rate. So I want mass flow rate per injection. So the mass flow rate injected per cycle divided by fuel injection time. So that will give you the your fuel injected per injection per unit time you will get. Okay. So the mass of the fuel injected per cycle I have to calculate. This is your total mass flow rate. Okay. So this is given in terms, total mass flow rate is given in terms of kg per second. So mass of fuel injected per second. This is total mass of fuel that is being injected per second. Divided by number of cycles per second will tell you the mass of the fuel injected per cycle. Okay. So this is the total amount of fuel that is being total mass flow rate of the fuel in unit second, and that divided by the number of cycles will give you the mass of fuel injected per cycle. Okay. So the number of cycles, how will you calculate? RPM is given, right? And if you divide by 60, we'll get revolutions per minute, right? And there are 2 revolutions for 1 cycle. To complete 1 cycle of operation, 2 crankshaft revolutions are there. So the number of cycles are going to be the speed of the engine divided by 60 into, at the denominator we are having 2. We have to divide it by 2. So that comes around 20.833 cycles per second. That means the engine is completing 20.833 cycles of operation in 1 second. Okay. So this we have calculated. That is at the denominator, number of cycles per second. Now we have to calculate the mass of the fuel injected per cycle. So that we have to calculate. So that is this divided by this. 2.0833 in 10 power minus 3 divided by this. That will give you the mass of fuel injected per cycle. So mass of fuel injected per cycle is this much quantity, right? So 0.1 gram per cycle. Okay, 0.1 gram per cycle. This is the amount of fuel injected per cycle. Now to convert this in terms of seconds, the time taken for fuel injection, right? See, the time taken for fuel injection, I want to calculate. The engine speed is 2500 RPM, which is 41.666 revolutions per second. Dividing by, if you divide this by 60, then you will get 41.666 revolutions per second. So this engine completes 41.666 revolutions in 1 second, right? And this one revolution is nothing but, in terms of crank angle, one revolution is nothing but 360-degree crank angle, right? So the total crank angle covered is 41.666 into 360. This is the total crank angle turned, right? This is the total crank angle turned in 1 second by the engine. So this crankshaft, the crank angle turned in 1 second is this much. But remember, what is the crank angle turned for fuel injection? It is given in the problem that for fuel injection, the crank angle turned is only 25-degree. This is the total crank angle turned in 1 second. This is the crank angle turned during fuel injection. So the time taken for fuel injection is, if you 25 into 1 divided by this term. So that comes around, the fuel injection time, it is around 0.00167 seconds per cycle. Okay, this is the time taken for fuel injection. And if you want to calculate the fuel injection rate per injection, right, then it is the mass of fuel injected per cycle, right? Mass of fuel injected per cycle, this we have calculated, 0.1 gram already we have determined, right? So, and divided by the time taken for fuel injection. Time taken by for fuel injection is this. This is the mass of fuel injected per cycle. This is the time taken for fuel injection. So that gives you the mass flow rate of the fuel injection, right, which is 0.0598 kg per second. So this much quantity of fuel is injected. At this rate, fuel is injected during the fuel injection process. This is the rate at which fuel is, okay. So the mass flow rate of the fuel injected is given as rho A into V. So density of the fuel is given. So cross-sectional area is pi by 4 d square, and velocity of the fuel flow is CD into root 2 GH. So to calculate this, you should know the value of CD. To determine the value of CD, the expression in terms of L by D is given. So if you substitute the value of L by D as 4 in this expression, then you will get the value of CD. So value of CD is known. So if you know the value of H, you can find the value of velocity of flow. So this H is expressed as pressure of the injector minus pressure in the cylinder divided by rho. And this G and this G will get cancelled. Okay, this is what is given in the earlier lecture slide I have given without G. Okay, because this denominator G and numerator G will get cancelled. So if you substitute all this, it comes to around 125.67 meter per second. This is the velocity of fuel flow. So now you know the velocity of fuel flow, you know the mass of fuel injected, you know the density of the fuel, you can calculate cross-sectional area of the orifice. So the cross-sectional area of the orifice is nothing but pi by 4 d square into 4. Why? There are 4 holes. In the injector we have 4 holes, right? So this is the total cross-sectional area. So from this you can calculate the diameter of one hole, right? So diameter of the one hole is 0.4164 mm. So what will be the length of the nozzle now? What will be the length of the nozzle? L by D is given as, what is the value of L? L by D is 4. So L equal to 4 times D. So if you multiply by 4, then we will get the length of the nozzle. Okay. Are you there?